All right, so we're going to go over Archimedes' principle in buoyancy, and this will be really helpful for the lab that we're going to be doing coming up here. So you guys are very familiar with this in your everyday lives. It's just that you may not quite have thought about why and how everything works. So we'll address that today. So buoyant force is the upward force that keeps an object immersed in or floating on a liquid. So if something is buoyant, it tends to be able to float. So Archimedes was a guy who kind of messed around with buoyancy and fluids and tried to do experiments and such. So he said the buoyant force of an object in a fluid is an upward force equal to the weight of the volume of the fluid that the object displaces. So that sounds kind of complex, right? When we talk about something being displaced, it's moved out of the way. So what happens, think about a boat going into water. When the boat is set on the water, it actually moves water away. So it displaces water. And so when we think about buoyancy, we have to address this idea of there's a force that the water has on the object, right? And if it's an equal force to the weight of that object, then the object is going to float. If the object is more massive, right, and the buoyant force isn't enough from the water, it's going to sink. So we'll kind of address some of these pieces today. So he studied fluids, and this was a picture from your reading. There's more pressure at the bottom of an object because pressure increases with depth. So there's this upward buoyant force on the object. So they're just kind of showing you that there. So weight definitely affects buoyant force, right? Especially density, right? So obviously the heavier something is, the harder that buoyant force is able to try to counteract it. So if the weight is greater than the buoyant force and the amount of fluid that it displaces, it's going to sink. So if we think about how we hollow out a boat, obviously, you know, if you have something that's got more surface exposed, that's going to make a difference. So we'll talk about that too. So if it's equal, it's going to float. If the buoyant force is more, it's going to be kind of buoyed up. If any of you guys have ever tried to like sink a beach ball in the water in a pool or in a lake and let go of it, it kind of flies out of the water, right? So the buoyant force is way more than the weight or the amount of water that it can displace. So this was a picture from your reading, right? And this gives you kind of an idea. Weight can be kind of tricky to mention all the time. We also have to think about density, and I'll talk about that with a steel ship and a steel block in a little bit. But for our purposes here, let's talk about weight. So they show you a duck. It's 9 newtons, and the buoyant force is 9, so it's going to float, right? But fish can float at different depths because of their swim bladder, which we'll talk about. So the weight of the fish is 12 and the buoyant force is 12. And so it's going to float, but it can address its buoyancy differently with its swim bladder. And we'll mention that in a little bit. Now the rock is 75 newtons and the buoyant force was only 50. So it's going to sink. So there again, if you were to flatten out this rock, right, and it still weighed 75 newtons, but it could displace more water by its shape, you might see a different outcome happen because of that. So the same applies for air because air is a fluid, remember. So helium is less dense, lighter than air. So we put helium in balloons because helium is less dense. It floats on top of air, right? So they rise up above the air. And this is kind of what I was talking about with a rock. So your book talked about, or the reading that you had talked about, a steel block versus a steel ship if they have the same mass. So say they're both 5 newtons, let's just pretend, right? So if we hollow this steel piece into this shape that's going to push, right? Push more water away from it. It's going to displace or move more water out of the way. It's then going to increase its volume, right? Even though it has the same mass. So you're going to end up making it less dense, right? Less mass per unit of volume than this, you know, condensed steel block here. So you're going to see the steel block sink because it's more dense. If you hollow this out, you have less dense, even though it's the same mass, and you displace more water, and therefore it will, in fact, float. So they're just showing you an example of that. So these are important things to keep in mind. It's not just weight, it's also density. So submarines, how do they work? Well, they deal with density even though, you know, a submarine is going to have the same mass, right, the whole time, if it fills the tank with water, it's going to be more massive. So that's going to change its mass, right? And so it can either fill the ballast tanks, these side tanks, with water. Obviously, that's less massive than air, or excuse me, water is more massive than air, or it can fill it with air and rise to the top. So what happens is, if it's floating on the surface, right, they're filled mostly with air. If it's going to climb down to deeper depths, they're going to fill the ballast tanks with heavier water so that it can do that. So it's really patented after the swim bladder in a fish, which we're also going to talk about. So it's also called a gas bladder, and we learned about this a little bit last year when you talked about fish, but they have this gas bladder that they can inflate or deflate, and if they inflate it, it makes them more buoyant, and if they deflate it, they're more dense, and so they can sink down to different depths based on, for example, in the winter, they like to swim at lower depths and such. So that's going to be important also. The only other thing I want to mention is we should think about all of these concepts in different ways. So, you know, these are just a couple examples that your book gave, but when you think in terms of all of this, think of fluids as in, you know, air and gases. So that's important to remember. Okay, let's come back together.